Good afternoon, everybody. My name is Peter Henley. I'm from the Water Research Centre in the UK. And my presentation today is to really try and outline some innovative thinking we've been doing on trying to tackle a 20th century problem, that of combined storm overflows in our combined sewer networks. And hopefully I can shed some light on the work that we're doing currently, and with a project that's actually in the process of being installed at the present time. Yes, so the title of the presentation is the WRcSO, and we're rethinking the CSO design for the 21st century. For those who are unaware of WRC, we've been in existence now for over 90 years. Originally, we were founded as a government research body looking at all aspects of water. Initially, water treatment for clean water supply, but much more latterly into foul water, wastewater, etc. And we've been, as I say, ongoing now for, I'll flick forward, for over 90 years. So we've got quite a history. We've written a lot of standards. We've worked collaboratively with our European partners as well. The problem we're trying to tackle is the problem of combined storm overflows on our combined sewer network. The problem with them is that they're aesthetically ugly when they work. They're required in the system to manage exceedance in terms of wastewater, particularly with wet weather events and managing that discharge. However, standard CSOs are often unpowered, and therefore any debris that's carried in the flow is presented to the screen to try and prevent it going into the watercourse. If it's not captured by the screen, it'll be passed forward into the watercourse and into the environment, and therefore is aesthetically unappealing. And this modern day 21st century, it is, for a water company, it's not the image that we want to be presenting to our customers, that we're polluting the environment in this manner. So we need to try and tackle that. Screens can often become blocked as well, if they're unpowered. That requires frequent operational maintenance. So people go into site and cleaning the debris away to make sure that they're functioning. Because if they're blocked and blinded, then the flows will eventually cause flooding upstream, and such as external flooding or even worse, internal flooding into customers' properties. And that's something we're desperately trying to avoid. So, as I've said, we're desperately trying to prevent the problem of sewer debris, litter being presented to the environment. So the challenge that we've got was to try, well, the impact of this is that we get a lot of customer complaints. And certainly in the UK, we're faced with an environmental regulator that is increasingly looking to penalise those who pollute. And now they've got a sliding scale of pollution fines that matched by company turnover. So a company such as Thames Water, the largest water company in the UK, has a multi-million or billion-pound turnover. The fines are scaled according to that turnover. So from small slap-on-the-wrist fines of 20 to 30,000 pounds or 20 to 30,000 euro, they're now in the region of £1 million per event. And Thames Water was certainly penalised and fined by the regulator of up to £20 million working back 3 years ago. So there's a real emphasis for the water companies to tidy up their act and to prevent this sort of incident. We've also got the water companies are regulated in the UK by the environmental regulator and by the industry regulator, Ofwat. And one of the scores they're measured against is the customer interaction. particularly negative customer interaction. So the water companies are penalised if they get unwarranted customer interaction with them. So telephone calls in, reporting a problem are seen as a detrimental impact on the business. So therefore, impact on the business in terms of the reputational, but also a financial impact as well. So it removes value off the share price of these private water companies. And that's, again, something their investors are looking forward to, making sure that the managers of the assets are managing the system correctly. So the challenge that we've been looking at, and we think we've finally overcome, is to allow the hydraulic process to occur at the CSO. So the CSO retains water in the system and then discharges exceeding flow out to the environment. However, the task is to try and retain the sewer litter within the flow, and then also try and prevent the sewer litter being presented to the CSO screen, and therefore removing the impact of any required additional operational maintenance visits. So WRC, my colleague Frank Moy, who doesn't like public speaking, and therefore I'm stood here in front of you, designed a CSO that retains the sewer litter within the network, but allows the flow to discharge. It provides a CSO solution that requires no power. So it's not a powered solution, so we can work in remote areas away from electricity supply, and therefore we do not need a powered screen. The benefits are that it significantly reduces the aesthetic pollution, the sewer debris being passed forward into the environment. And it also has the positive impact of reducing the times that people have to visit the site to clean the screens. And we're looking at a modular construction as well. So it's designed and built off-site, and then it's brought in and then installed. So it's a very quick process. It improves the speed of installation and therefore a considerable cost saving. So the solution is, we've come up with an innovative two-chamber design. Chamber 1 is the largest system, and it separates the floating debris and it returns it via a bypass pipe to the downstream sewer. Chamber 2 is where the CSO facility is, and therefore once the flow levels reach a certain point, it will spill. However, Chamber 1, if it's functioning correctly and is designed well, will have captured all the floating debris, and therefore there will be no debris presented to the screen that could lead to it being blinded or blocked. And more importantly, there'll be no sewer debris being passed forward into the environment, which is something we're very keen to avoid. So on the screen here, I've got my pointer. We've got two chambers. This is the first chamber. And as the flows pass forward through to the orifice, which is restricted, and is designed to be much smaller than a standard CSO, the sewer debris is captured in Chamber 1 and then passes forward. So we've got a bypass pipe here, which is set below the level of the actual CSO spill point. So that means any floating debris in the chamber will be captured and passed forward into the bypass point and taken on down. So the pass-forward flow is calculated on the size of the orifice, allowing the continuation flow, and also the continuation flow from the bypass pipe. The positive thing from the bypass pipe is that it collects the floating debris. The two chambers work on a U-shaped principle, so as the levels rise, they both stay the same. However, the spill at the CSO only occurs after the bypass point has been reached, and therefore there's no floating debris ideally in chamber 2. And we've done some CFD modeling of the system, and hopefully if this video works. All right. Hopefully. Working? Yeah. You can just about see the flows there with the floating debris represented in the multicolored points. So as the flow rises, the chamber here is the chamber 2 where the CSO is. The debris is contained within chamber 1. There's very little debris being passed forward. It reaches the spill point and down into the bypass point, and therefore it can continue down into the sewer and is retained in the sewer network. As the flows drop, again, the flows drop down and the sewer debris is contained within the flow. And therefore, flick again. So again, a slightly different view. But as the flows rise, we've got our bypass spill point, our overflow spill point. So the floating debris is contained within the chamber 1. It reaches the spill point and will then spill over into the bypass point and forward into the flow, containing all of that debris, floating debris within the pipe. So this is, as I've said, this is an unpowered system. It's operated purely on hydraulics. It maintains the integrity of the overflow screen. It doesn't require routine, regular operational maintenance. And the calculations we've done is that 98% of the sewer debris is retained within the system, which is considerable benefit. And therefore, we're not going to have debris being presented to the screen and also discharged in extremis to the environment. So just to summarize, the advantages are that it reduces debris presented to the screens by 98%. It reduces the impact of aesthetic pollution. It's a passive, unpowered system that can be retrofitted. There's no electromechanical maintenance costs. So with a powered system, obviously you need to routine annual maintenance. That's not required. And there's a reduced incidence of customer contacts to the water company, and therefore the company is less likely to be penalised. The system reached or received its patent on Friday, which is very good news to WRC, having told you all our ideas. And as I say, the first design, or the working design, is going into the ground as we speak. It'll be up and running by the end of March, so just in time for Brexit. So that's me. Thank you very much for listening. Catch me anytime for calls.